I chose a system of 3 times 3. First equation like so, second one like this, and this one is like so. I think it's one of the systems we just, when I first discussed with you the Gaussian elimination, if I'm not mistaken, that's the system which I used to show you the Gaussian elimination method. In that case, the system has a unique solution, and now I'll test the Cramer's method on this system. So the principal one is when I take the left-hand side and build a matrix out of it. Here's my principal determinant. Let's compute that. Say we go row decomposition. So it will be 2 times, here's my minor, which is -1, -2, -3. So it's -6. -6. Now I move it here. -1 plus sign alteration will make it +1. So we can easily disregard this factor. The remaining minor is a column. Here's a column, so it is across this diagonal it's -1, across this diagonal it's -3, so it's -4. So it's another -4. And now the last one, it is 1. Again, nothing to actually remember. And this minor gives me 2, take 3, it's -1, so it's another -1. Here's my determinant. You see, you can be very efficient when you compute this if you do the minor method. So the determinant is 11. Just move the cross out. The determinant is 11. I no longer need this. The determinant is 11. It is non-zero. It's a clear sign we have a unique solution. Now we have to compute the determinants, 3 of them, associated with each of the unknowns. So what do? I take my principal one. I cross out the first column, and I fill it with the right-hand side. That will be the determinant corresponding to the first unknown. Here it is. In fact, it's very often convenient to, rather than saying delta 1, delta 2, delta 3, they use as a subindex the actual name of the unknown you're looking for. It is just because here the unknown was x1, if you will write delta subindex x subindex 1, it will look a little bit ugly. That's why they put just 1. But when you have like a name without indices, x, we better use x for that. So here it is. First column replaced with the right-hand side. Let's compute that. So that will be -1. Sorry, my fault. I need to compute the minor first. Minor is -1, -2. It's -3. So altogether it is 3. Together with this -1. Then comes this 1 plus sign alterations, another negative. Here's my cross now in this. No, sorry, it's actually -1. So it's -1. Sign alteration makes it 1. So we have 4 and -1, -4, and plus 2, it's -2. So it will be -2 then. And now I move my cross here. The minor here, 8, plus 2, it's 10. So it is plus 10. So it is 11. 11. Already now I can tell you what will be the x value in my solution. It will be 11 by -11. It will be -1. Let's just now open delta y. Here's my determinant corresponding to second unknown, to the unknown y. This one is built by crossing this column out and filling with the right-hand side. Again, I'm going to use the first row for my decomposition. I no longer need this one. This is gone. If I use my first row for the decomposition, that will be 2 times the minor, which is -4 plus 2. It's -2. So altogether -4 for the first term. Here comes my cross in the second position. 1 together with sign alteration. -1 and -3, -4. So another -4. And here we have -2 and -12 and -14. Is the terms for this decomposition. Together they make -22. And that is the value for the second determinant. And now I know the value for the second unknown. It's a quotient of negative 22 by negative 11? 2. Final one, delta z. Well, because we just went so far computing this, I'll finish this computation as well, just to show you that sometimes I finish things. So this is my delta z. Again, I will use the first row. I'm very consistent this time. If I use the first row here, 2, and here's my minor. Negative 2 and negative 8. It's negative 10. So altogether, it's negative 20 for the first term. Here's my negative 1. Again, sign alterations makes it sign alteration makes it 1. The remaining minor is 1 times negative 2. Negative 2 and negative 12, negative 14. And the final one, it's negative time this time. It's 2 take 3. It's negative 1, so it is plus 1 in fact. Easy computation for the last determinant. Altogether, this is negative 33. Negative 33. And so my last unknown, z, will be the quotient of this determinant of negative 3 by negative 11. So here it is. My x is this quotient, my y is this quotient, and my z is this quotient, which are negative 1, 2, and 3. We can double check, of course. I mean, when you come up with such beautiful numbers, it's very unlikely they will be wrong. I mean, when you come up with the integral solutions, it's very unlikely it will be wrong, but still double check is always in order. If you can do a double check in any way, you have to do it. It will save you lots of time and nerves. Let's just do it. Negative 2 plus 3, negative 1, that is correct. Negative 1 plus 2 plus 3, 4, that is correct. Negative 3 plus 4, take 3, that is correct.